Hello and welcome to the first lesson on the Intro to Sequences and Series. Sequences are going to be some sort of collection that has some sort of order involved in it. So like a first item, a second item, a third item, so on. Some examples that are non-mathematical that we're used to are like the months, so we have an order to them: January, February, March, April, May, and so on. And if someone were to say them to you out of order, you would notice that something was wrong, right? If I was like October, July, December, August. Did I already say August? I don't even remember. See, can't even do it. All right. So sequences, some sort of order involved. In math, that's going to be a set of numbers that are written down in some sort of specific order, and they most likely follow a very specific pattern. All right. Each individual number inside of one of these sequences is called a term, and we refer to them as like the first term, the second term, the third term, the eighth term, things like that. So, for example, in this finite sequence, and finite just means that it ends, 2 is the first term, 4 is the second term, 6 is the third, and 8 is the fourth. In an infinite sequence, it just goes on forever and ever. That's what this little, dot is saying there. Now, when we're talking about the domain of sequences, which is, the inputs are that term number, right? So like 1, because this is the first term, 2, because this is the second, 3, 4. And so that's our input, is the actual term number, which means when we go to write like what the pattern is, you should be able to figure out like a specific term, like what the 100th term is, because the rule or the pattern is going to involve that 100 somehow. And then if we were trying to find like the 30th, it'd be the same thing. That rule or pattern that we're using, we would be able to use the 30 to figure out what the 30th term is. So because of this input that we have going on here, and we can't ever get a different output from it, that means that technically sequences can be thought of as functions. Now, there's pros and cons to thinking of sequences as functions, and there's pros and cons to not thinking of them as functions. So we're going to introduce the notation as if they're not functions, and then periodically I'll be telling you like how to connect it back to what a function would be. So rather than using f of x, we use this a notation that you can see down here in the middle here. So a1, a2, a3. Officially, it's like a sub 1, a sub 2, because they're subscripts, but most of the time we don't bother saying the sub part of it and just say like a1, a2, a3. And that literally stands for the first term, the second term, and the third term. So if I jump back up here, this number 2 right here, that is a1. Okay, so the little 1 is telling us that it's the first term. So the 8, that's going to be the fourth term, so it's a4. So literally we can say a4 equals 8. And in function notation, that would have been like us saying f of 4 equals 8. So the little 4 is kind of like what our x value is, but we don't use x's in sequences and series. We use the letter n, okay? So in this case, we would be saying that n equals 4. N is the term number, okay? So n is 4, and then the fourth term is 8. So it's similar to function notation by saying like f of 4 equals 8. We're saying a4 equals 8. We're saying the same idea. When you input 4, you get an output of 8. Now, this last thing that's here, an, we can think of this actually in 2 different ways. So the first is that it's sometimes just the end term. So when let's say I have some random sequence, and I'm going to not be too random with it. Let's say it goes like this, but then it keeps going for a while and then goes here. Now, I don't know off the top of my head, like what is that term number, right? Because I know that this is the first term, this is the second term, this is the third, but then I don't know how many are in between without doing a little bit of math. So this is the nth term, which means that we refer to it as a sub n. So we would say 13 is a sub n right now because we don't know what the last term is. Like we don't know its number, like that it's the 7th in the pattern or something like that. So we call it an. So it's the ending term. It is also the rule or the pattern. And this is basically another fancy way of just saying like the equation that you're using in order to figure out what the outputs are. So if I look down here at example 1, we have a sub n equals n squared plus 2. That is a rule. Okay, so a rule is basically an equation that has n involved in it, and it tells us how we're actually going to figure out what the numbers are in this sequence. So if I want to find the first 4 terms of the sequence, I'm going to do a1, a2, a3, and a4. And when I'm doing this, what's important to remember is that whatever this little subscript is, that's what n is. So when I'm writing this little a1, I'm saying, hey, n equals 1, and n equals 2, and n equals 3, and n equals 4. And so then when I look at what the actual pattern is, which is n squared plus 2, I know that wherever there's an n, I'm putting in whatever this little subscript is. So for this first one, I'm going to be doing 1 squared plus 2 because my n value is 1 right now, and that's going to equal 3. In a2, I'm saying that n equals 2, so then I'm looking at the rule and it says do n squared plus 2, so that's going to be 2 squared plus 2, which is 6. On a3, I'm saying that n is 3, so this is going to be 3 squared plus 2, so that's going to be 11. And then when I do a4, that's going to be saying, hey, do 4 squared plus 2, which is 18. And so the first 4 terms of the sequence are 3, 6, 11, and 18. I hope that made a tiny bit of sense. We're going to do it again with this one, maybe do it a teensy bit faster. So now that we kind of understand that the little subscript is saying what n is, and I just plug it into the formula for it. So I'm going to get 1 over 1 plus 1, so that's going to be 2. When I plug in 2 for n, I'm going to get 2 over 3. When I plug in 3 for n, I will get 3 over 4, and then I will get 4 over 5, and so on. So whatever this little tiny subscript number is, that's what we're saying n is, right? N equals 4, and then we just plug it in to whatever the rule is. All right, so I have your turn for you to practice. You should pause the video and, see if you can figure it out yourself. And I will do it in case you get a little bit lost. Alrighty, so I'm just letting n equal 1. So if I do 1 minus 1 over 1, that's 0 over 1. And remember, if you have 0 on the top of a fraction, that's always 0. If you have 0 on the bottom of a fraction, that's undefined. That breaks math. All right, a2, we're going to end up with 1/2 when we plug in n equals 2. For a3, we're saying n is 3, so we're going to get 2/3. And then a4, we will get 3/4. So this pattern goes 0, 1/2, 2/3, and 3/4, and it's very similar to this one that we just did here, except that everything is shifted. So there are ways for you to take patterns and kind of shift it so that it starts at a later point. So here we had that 1/2 was the output for 1, yet here we were able to get that 1/2 was the output for 2. And we could keep modifying it if we needed to make like the output be 1/2 when we're at 4, and so on. All right, for this one, we're going to get this cool alternating pattern because when I do -3 to the first, because remember, n is 1 here, I'll get -3. When I do a2, I'm saying that n is equal to 2, so that's still a 3 there, and that's a 2. I'm going to get +9 this time. a3, I'm doing -3 to the third power, that's going to be -27. And then a4, I'm doing -3 to the fourth power, that's going to be back to +81. So we get this fun alternating pattern that's happening here, negative, positive, and then each time we're multiplying by 3, right? 3 times 3 is 9, 9 times 3 is 27, 27 times 3 is 81, and kind of so on. So I'm hoping you're kind of getting a feel for what things are looking like here, and we're going to get into slightly harder stuff now, which is working backwards from what we just did. I'm going to give you, here are the numbers of the sequence. Can you tell me what the rule is? So can you tell me what the pattern is that's happening here? So before we do that, there are some distinct patterns that happen more frequently than others. So for example, the first most common pattern we have is that you just add something each time, right? So you add 2, add 3, add 4. So, when I was doing that pattern, 1, 3, 5, ... and whatever, I was adding 2 each time to the pattern, right? So the next one would be 7, then I'd add 2 and get 9, and then 11, and so on. That one has a specific name. It's called arithmetic. It's kind of like arithmetic, but we just pronounce it a little bit differently. So arithmetic, and that's what the next 2 lessons will be on, that type specifically. The next most common one is when we multiply by a constant. So that's what we just did here in part B. We multiplied by -3 over and over and over. And that one has a specific name. It's called geometric. We'll spend the next 2 days after arithmetic doing that type. And then the last one that's really popular is when each term is raised to a particular power. So that's going to be more like what we did kind of over here, where we did like n squared plus 2, where we're raising it to a particular power. And I don't think that has a special name, but my guess is that if it did, it would be called like a power sequence, which, I mean, that sounds like a legitly cool name, right? Like, hey, let's do the power sequence right now. You know, that's like cool. All right, you can make fun of me in the comments below. Oh my God. Hey, while you're at it, drop a like, you know, crazy, whatever. All right. Sorry, cheesy YouTuber. I don't know. I'm trying or pretending. Who knows? Let's get into it. For this given sequence, we're going to try to describe the pattern. We're going to try to write what the next term would be, and then we're going to write a rule for it. All right, and I'm going to ignore that hint for the time being and have us just look at this. So we have e squared over 2, e3 over 3, e4 over 4. So the next term in the pattern is going to be e5 over 5. And hopefully that makes a little bit of sense to you. If I kind of divide this up and make it into like a little table, which I kind of ran out of room because I wrote a little too big there, my bad, but this would be the first term, this would be the second, this would be the third, and this would be the fourth, and then we just did the fifth. And when we do that, it makes it a little bit easier for us to make the connection to say like, hey, what is this general pattern that's going on? And if I look, when the term number was 2, I was doing e to the second over 2. When the term number was 3, I did e to the third over 3. So if the term number was n, meaning I don't know what it is, then it's going to be e to the n divided by n. And that's going to be our rule. So the way we write that is we write a lowercase a sub n, but our lowercase a is kind of written almost like it's the same size as a capital. Like if you were to write a capital A, except that you very specifically use a lowercase a, not a capital A. And then we say equals, and then we just write that e to the n over n. So this is referred to as the rule, and it's basically describing what the pattern would be. All right, the next one, my first thing is I would try adding, right? So if I did 2 plus 2, that would be 4, but if I did 4 plus 2, well, that's not going to equal -8. But then I realized, oh wait, this was actually -2, so I actually added 6, but if I add 6 to 4, I'd be at 10. So I'm not adding. So next I'm going to think about multiplying. And it does kind of look like if I look at just the numbers and ignore the negative signs for a second, that I'm multiplying by 2 each time. And if we remember back to earlier lessons, when you multiply by something over and over and over, that's kind of like the definition of what an exponential function would be. And this is going to be what a geometric sequence is when we get into it. But what I can basically do is say, hey, it's not just multiplying by +2, which is what it would be if we were working with functions. It would actually be -2 that we're multiplying by each time. So the next one in this pattern would be -32. And what I think is happening is I'm doing -2 raised to the nth power. And so the way I'm going to check that is, remember, like this is the first term, this is the second, this is the third, and this is the fourth. And if I did 2 to a power, so 2 to the first, that's 2. 2 to the second, that's 4. 2 to the third, that is going to be an 8. And 2 to the fourth would be 16. And then if I pay attention to my negative that was in there, every time that I have an odd exponent, it will stay negative. And every time that I have an even exponent, it will become positive. And that makes sense because if I have an even number, I'm going to cancel out all of my negatives. When I do like a negative times a negative, cancels. Negative times a negative, cancels. And so on. So our rule this time around is going to just be an equals -2 to the nth. Now, as a little sidebar, if we were doing this as a function, first of all, we wouldn't be able to because bases cannot be negative or 0 or 1. But let's just pretend. We would say, hey, our initial value is -2, and our thing that we're multiplying by is -2, and we're doing this to just the x. I don't know why I wrote -1 there. I mean, I do, but that's a future us thing. And so you can see that things are a little bit different here, because if I let x and n be both 1, then I get -2 and I get -2. So that one works. But when I let x equal 2, this thing breaks on the bottom now. I'm going to have -2 times 4 is -8. And so when x was 2, it actually bypassed what was happening. And also in functions, we could go 0 and we could go negative, and we can't do that with sequences. It has to be 1, 2, 3, 4 as our input, our n value, our x value. So just wanted to make that connection that these guys are similar but different. All right, so here we have a your turn for you. So you should pause the video, you should try it, and then as always, I will be here when you're done with that to try to figure out, you can check if you're right and also see what's going on. All right, so hopefully you pause the video, and I'm going to connect the term number again. So we need to remember that this is the first, second, third, and fourth term. So if I make a guess what's happening with the fifth term, I would say my guess is that I'm doing something like this. 1/5 times 6, because each time I look at it, the number not in the parentheses on the bottom is the same as the term number, and the one in the parentheses is one bigger than the term number, and the top is always 1. So I think my rule is going to just be a 1 on top, and then whatever the term number is, n, times just one more than that, so n plus 1. And so this would be my rule. All right, with these fractions, what first jumped out to me right away is the top. I can just do times 2 on top, and on the bottom, I'm just doing times 3. So right away, I'm saying, hey, I'm going to have something like 2/3, and then I'm doing it repeatedly, so probably to the nth. But I do want to just check that if I'm at the first term, do I get 2/3? Yes. If I'm at the second term, I would be doing 2/3 squared, so that would be 4/9, so that works. So I do think that I actually just have the rule right now. And I totally missed writing what the next term would be. I guess that would be 32 over, I'm not good at doing math in my head, but I think it would be 243. I don't know, we'd have to check in a calculator, but that would be the next term in the sequence. All right, so what you're hopeful for is that they're nice like they were in A, where they didn't actually write out what the multiplication was, because they could have been mean and they could have said, hey, the pattern is 1/2, 1/6, 1/12, 1/20th, and then like 1/30th, and it would be a little bit harder for you to figure out that you were doing n times n plus 1 on the bottom of the fraction. So they sometimes are nice and they leave it separated so it's a little clearer what the pattern is going to be. And then other times, like in B, they think that the question has decided that the pattern's easy enough for you to follow that you don't need to do it like this. All right. I think I'm just going way slow, but hopefully you're okay with that. You can always speed the video up. But whatevs, we're going for it. We can find a sequence in the calculator by following these steps, and I'll show you in a second. But we hit second list in the calculator. We move over to operation, so ops, and down to sequence, SEQ. Now, depending on how old your calculator is, you might have to follow what this step is, which is you write your rule. You say that your variable is going to use x because we're going to use x. And then you say what term you want to start with, so like the first term, or maybe you want to start in the 7th term. And then what term you want to end with, so like the 4th term, or maybe you want to end on the 10th, and then you hit enter. If you have a newer calculator, it's going to look a little bit more like what I'm about to show you here. All right, so I'm going to hit second and then list, which is that one that's highlighted red right there. I'm going to move over to operations, okay, and I'm going to go down to number 5, which is sequence. Okay, so I'm going down to number 5, sequence. So newer calculators look like this. This first thing is your expression, what your rule was. So let's do what we just did, which was 2 divided by 3 raised to, so I used the little exponent there, and I'm going to use x. Remember that x is easiest to find by right next to alpha. That's just because getting n is annoying. We'd have to hit alpha then n versus just hitting x. So it's really pure laziness that I don't use n. For the variable, I'm going to say that the variable was x I put in there. Let's just do the first term to the 4th term. Now, newer calculators have this step thing, and that's basically because they decided that in rare cases you might choose to allow 1.5 or 2.5 or something like that, and so you could make your step be smaller. We're always going to be a step of 1. And when I hit paste, this is what an older calculator would look like before they hit enter. So they would have the expression, comma x, comma 1, comma 4, and then you don't need to put that last comma 1 if you have an older calculator. And it gave me this bunch of fractions. I can't really see what's going on. You can scroll by hitting your arrows left and right, but I'm going to hit math and then enter to turn this back into a fraction. And here we go. 2/3, 4/9, 8/27, and 16/81, or however you would pronounce that. And so what I just did is I confirmed actually that our pattern that we made here, 2/3 to the nth, was actually right because I got what I was looking for. So that's a good way to check your work, or if you don't want to have to do the crazy math involved in writing out the sequence, you can ask the calculator to do it for you, and then you just write your answers down. All right, next one we got is a little bit confusing. And we have what's called recursively defined sequences. So up above when we had these ones, like let's say that we were in this one. If I asked you, hey, what is A100? You would be able to say, hey, that's going to be 1 over 100 times 101, and then whatever that is. And that was easy for you to do. And that's called an explicitly defined sequence. There's these other type that are called recursively defined. And recursive, I don't know what the right word is, but this recursively defined thing, it's used a ton in programming and computers. And what it's basically saying is you use whatever your previous output was to help you determine what your next output would be. So let's just take, for example, I have some rule that says, hey, take your last answer, okay, so your last output, whatever that was, and I want you to just, add 3 to it. So this is kind of a really easy one, but, just add 3 to it. So let's say that our previous output was 10. Well, then our next one would be 13. And now if we use the rule again, it says, hey, take your last output, which is now 13, and add 3 to that. We would get 16, and kind of so on. So we need to introduce a new way of thinking about the AN. It's not just the last term. We could also think of it as our current term. So the term that we are currently trying to find. And let's say that was A5. Then what term came before A5? It would be A4. So the way we can write that with notation here is to do AN minus 1. And then this would be what the previous term was. And if I wanted to keep going, I could do AN minus 2. And this would be the previous term. And you could just keep going for as many times as you wanted to. And what I'm basically doing here is saying if A5 is me saying that n equals 5, then if I do AN minus 1, that's going to be why did I write 4 here when I wanted to write 5? Man, my brain is not working right now. Apologies. If n was 5 here, then AN minus 1 is going to be 5 minus 1. Well, that's going to be A4, the previous term. And if I do AN minus 2, I don't know why I wrote it so high. My bad, it's still in the subscript. That would be like doing A5 minus 2, which would be A3. So if I'm on A5, the previous term was A4, and the previous term was A3, and I'm basically just taking n and subtracting 1 or subtracting 2. Some people have a little bit of trouble with this, so it's okay if you're a little confused at first. So here they want us to write the first 4 terms of this recursively defined sequence. And if I look over here, here is what the rule is. So let's kind of break this down. We have AN equals n. So we're doing whatever our current term number is, and we're multiplying that by a sub n minus 1. And remember that that is our previous term, whatever it was. Not its term number, what the previous term actually was. So if the previous term was 10, then we would be doing times 10. Even if that was the third term in the sequence, we would be doing whatever it is. Now, what's kind of neat about these is that you need to have a starting value, because if your formula is written by what the previous term is, you need to know what a previous term is in order to start writing the sequence. So that is why they gave us A1 equals 1. And so if I want to find A2, remember what I'm saying here is that n equals 2. So if I look at this rule, I'm doing n times AN minus 1. So I'm doing n, which is 2, times AN minus 1. And if n is 2, then that's I'll write it here. I'm going to end up erasing it. But I'd be doing A2 minus 1, which is going to be A1. So I'm doing times A1. Well, what does A1 equal? We know that. It's 1. We have that right there. So this is going to be 2 times 1, which is 2. So the second term happens to be 2. And now your brain might be saying, hey, when n was 1, it equaled 1. When n was 2, it equaled 2. So is that going to happen when we do A3, where we're officially saying that n equals 3? Let's find out. Our term number is 3. And then if I'm doing AN minus 1, n is 3. So I'm going to be doing A3 minus 1, so A2. So I'm doing this times A2. And we know that A2 is really 2. So I'm going to get 3 times 2, which is 6. So it's not just, that n ends up being what the output is. It does change. And if I keep going and do A4, the term number is 4, and I'm multiplying it by the previous term, A3. So that's going to be 4 times 6, which is 24. And then we could keep going. Now, a weakness of this is if I were to ask you right now to say, hey, what's A100? You would need to know what A99 was in order to find that out, because you would have to do 100, right? 100 times what A99 is. Well, what's A99? you would need to know what A98 is. And to find A98, you need to know what A97 is, and so on and so on and so on. So that's like a huge weakness to recursive functions, is that you have to go through the whole process to get to the number that you're trying to find. Whereas the explicitly defined ones, the ones we had up here, we could just plug in 100 and figure it out. So that's like a huge strength to it. Now, there's one last thing I want to talk about that is a strength of recursive, which is, let's say instead of A1 equaling 1, what if I had said that A1 equals 2 this time? When I go to do my rule, the same exact rule, term number times the previous term, when I go to do this, I'm going to get 2 times A1, which is going to be 2 times 2 is 4. And then when I do A3, that's going to be 3 times A2. Well, A2 was, 4, so I'm going to get 12. And then A4 is going to be 4 times A3, and I'm going to get 48. And you notice how I just got a completely different pattern, but I used the same rule, which was term number times previous term. The only thing that changed is my starting value. So that's huge when you're trying to write things like systems, especially in computers, where you want it to do the same thing, but you don't actually know if it's always going to have the same exact input. Like maybe the computer is, the user is going to type in the letter E, and when I type in an E, you want them to do this. But if they typed in the letter H, you want them to do this same idea, but you want to make sure that you're using an H and not an E. So it's just like another way of doing things that has pros and cons. So big con, can't figure out what big numbers are without going through every single one. Big pro is you can completely change your sequence just by changing the initial value that you started with. Alrighty. You should pause video and you should try the your turn. Just before you do, real quick, I want to point out that we have an an-2. Remember that is our previous term. So 2 terms ago. And then we have an-1. That's just our first previous term. And you can see over here that they gave us 2 previous ones, because if we're using both the previous term and the previous term, we need 2 starting values in order to figure things out. All right, so give it a shot and see how it goes. Alrighty, here's A1 and it equals 1. A2 equals 1 as well. They gave us this to begin with. So what A3 is going to do, remember we're saying that n equals 3. So when I plug it into this little formula here, an-2 is going to end up being A1, and then an-1 is going to be like A2. And we know that A1 is 1 and A2 is 1. So I'm really doing 1 plus 1, which is 2. All right, when I do A4, I'm going to be doing the previous term. Well, that's A2. And then the previous term, which was A3. All right, so A2 was 1 and A3 was 2. So now I get 1 plus 2, that's 3. And let's just keep going, even though it only asked us for the first 4, so we can kind of get a better handle on this. If I did A5, that's going to be A3 plus A4, so the previous 2 terms, which would be 2 plus 3, and that's going to equal 5. And then when I do A6, well, that's going to be A4 plus A5. That looks like a 21. There we go. So that's going to be 3 plus 5. That's going to be 8. And if I write this out in like a different way, so I'm doing 1, 1, 2, 3, 5, 8 as I keep going, this is a very famous sequence that's called the Fibonacci sequence, which is you start with 2 1s and you add them together, and then you always add the previous 2. So I do 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is going to be 13, 8 plus 13 is going to be 21, and so on. And so that's what this rule looks like when it's written as a formula. Take the 2 previous numbers and add them together, and that gives you your new number. And that's the Fibonacci sequence, which is used all the time in things. If you're not really sure what it is, I suggest you just YouTube it, or I'm sure that there's like a, Wikipedia that you could try to read on it if you really wanted to. All right, we're almost done. We have ourselves series. So a series is just a really fancy way of saying that you want to take a sequence, so a set of numbers, and just add them up. So a series is basically a sum, all right? Meaning we added a bunch of things together. So literally it means take the first term, A1, add it to the second term, and then add that to the third term, and then add that to the so on, so on, so on, until you get all the way to however many terms you want to add up. And that gives you what your sum would be. Now, that's annoying to write it out like that. So we came up with a shorthand notation, which is called summation notation, all right? And what we do is we start off with this giant E, okay, which is a Greek letter, sigma. and it stands for sum in math. If you ever see this giant, Greek letter E, it means that you're adding something. Well, we start off with the bottom, this k equals 1, is we're saying start at this term number. Okay, so start at the first term because it's a k equals 1. If that had been like k equals 5, then it's saying start at the fifth term. The number on top is going to be your ending value, so your ending term. All right, so let's say that it started at the bottom k equals 5, saying, hey, start at the fifth term, and then the top was an 8. It's saying, okay, what I want you to do is start with the fifth term, figure out what that is, then add that to whatever the sixth term is, add that to whatever the seventh term is, and then add it to whatever the eighth term is, and that's going to be what your sum would be. So basically it's saying start at this term, end at this term, and add all the ones in between. This AK, this is just our rule, and we basically just changed the letter away from N to be K, and we sometimes use I for index, especially in programming. We use I and J for that, but we just changed the letter because officially we're putting the N on top. So we don't want to say like N equals 1 and then AN and then an N on top of the fancy E, because then there's just too much N's going on. So we just kind of changed the letter, and they don't always change the letter, as you'll see a little bit later on. So when we're reading this, this giant E, right, we say that we're doing the sum of the rule from k equals 1 to k equals n, whatever number's on top. All right, so for number 7 here, we want to express this as using the summation notation, so the giant E. So that's our goal. We're going to do this giant E, and we're going to fill it all in. So we have the sum is 5 plus 10 plus 15 plus 20. And so what I notice here is that I'm starting at the first term because they didn't tell me otherwise, and I'm going to stop at the fourth term because I'm only doing 4 things here. Now, to find the rule, we have to figure out what the pattern is that's going on here. So what I'm going to do is ignore the plus signs for a second, and I'm going to fill in the term number so I can look for connections here. Now, most people's first instinct is to say, oh, I'm just adding 5 each time. But you have to remember that our rule has n in it. So if I say like an equals just n plus 5, because you're saying I'm adding 5 each time, well, then this immediately breaks because this one would be 6 because n is 1. This one would be 7 because n is 2. And this one would be 8 because n is 3. So it's not n plus 5. That doesn't work. I've confused my computer. I don't even know if that shows up on the video, but it got confused. We're back now, don't worry. So what's actually happening here is if I look at connecting the 1, the 2, the 3, and the 4 to what's happening, what I notice is that if I did 1 times 5, that's going to equal 5. If I do 2 times 5, that's going to equal 10. If I do 3 times 5, that's 15. And I do 4 times 5, that's going to be 20. So what I think is actually happening here is I'm doing 5 times whatever the term number is. Term number, not turn. Okay, and we'll learn more about that because this pattern, when you're adding the same number over and over, is an arithmetic. That's what we do for the next 2 days, an arithmetic sequence. All right, when I go to write this, I just write 5k. And remember, I switched the letter to match whatever letter I have down here. So if I had said n equals 1, then I could write 5n. And this is it. That's what they asked me to do. They didn't ask me to actually find what the answer is. They just said, hey, write this in summation notation. All right, for 8. What they want us to do is write out what the following sum is and then actually find what the answer would be. So if we read this, we're doing the sum of n plus 1 over n, and we're doing this from the third term all the way to the 7th term. Alrighty? So let's figure out what the third term would be. I would do 3 plus 1 over 3. Okay, then the fourth term would be 4 plus 1 over 4, and then it would be 5 plus 1 over 5, and then 6 plus 1 over 6, and then 7 plus 1 over 7, and I'm going to stop there because the top number is saying stop when n equals 7. So I did n equals 3, n equals 4, n equals 5, n equals 6, n equals 7, and then because this is a sum, right, the giant E means sum, I'm literally adding these fractions together. So in my calculator, I would add 4/3 plus 5/4 plus 6/5 plus 7/6 plus 8/7, and I would get that's 853 over 140. And so that's what this sum would actually be. So this time they asked me to write out the sum and also find it. That's why I actually calculated it this time. All right, you should pause the video and you should try 9 and 10. And then we have one last thing to go over, which is how to do these in the calculator to help us out. So you should pause the video and try it yourself. I'm sure you did that. This guy right here, I'm going to start off with k equals 1. And then what I notice is there's a ... there. And so that means I'm going on forever and ever and ever. So what I'm putting up top is infinity, because I'm going forever because of these dot dot dots right here. Now, when I look at what the pattern's going on, 3 to 9 to 27 to 81, it looks like I'm just doing times 3 each time, all right? And so let's think about this again. And I just realized my answer key is wrong for this one. Oh boy, we'll have to fix that. If I'm doing, 1, I'm not just doing 1 times 3, because the next one would be 2 times 3. This would have to have been 6, and then 3 times 3, that would be 9. So what I'm actually doing is noticing that if I did 3 to the first, and 3 to the second, and 3 to the third, and 3 to the fourth, that this would work. So I believe if I was on the nth term, that this would be 3 to the nth power. So my little thing that I'm going to write here is 3, and again I'm going to use k because I switched to using the letter k in the summation, and that would be what my answer is. Whew, I got to fix that in the answer key. All right, here they want us to write out the sum and find the sequence of that sum. So I'm starting at 1 and going to the 6th term, and I'm doing k to the 4th power. So I'm doing 1 to the 4th, 2 to the 4th, 3 to the 4th, 4 to the 4th, 5 to the 4th, this is going to be a big number, 6 to the 4th, and I'm adding all of those thingies together. And when I do that in the fancy dancy calculator, I'm going to get 2,275. So that's what the sum would be written out, and also what it actually equals. All right, so hopefully you're feeling okay with that stuff. Let's just quickly go over how to do one of these sums in the calculator. So the first 5 steps are what you're going to do if you have an older calculator like a TI-83. Okay, so if you had to, when we did the sequence one before, if you had to actually write out like the expression comma x comma like 1 comma 4 or whatever in your calculator, and it wasn't like written out, like expression, variable, start, stop, you have to do steps 1, 2, 3, 4, and 5. Okay, so you define what the list is, and then you have to ask the calculator to sum that list essentially. Now, if you have a newer calculator, which is what I'm going to show you because I have the newer calculator, you literally just go to math and then you go all the way to the thing, and it has a summation with the little fancy e there, and you can find the sum. So I'm going to find the sum of this one right here and show you how to do that real quick. All right, so I go to math and I'm just going to scroll. I find it easier to scroll up, and I have summation with the fancy e. If I have this really fancy thing here, I'm going to again use x. So I'm going to say, hey, let's let x go to 1, then I'm going to have it go to 6, and my little rule there was that I was doing x to the 4th power, and if I just hit enter, I should hopefully get that same 2275. So what I'll do is I'm going to keep going with the video and show how to do it on an older calculator for you, but if you have a newer calculator, you're done. Congratulations. Go for the practice and see if you can figure this all out, and hopefully you found this helpful. Don't forget to like and subscribe, and I'll see you in the next one. All right, older calculator friends. What we are going to do is first do second list, and we're going to go to operations, and we're going to go to sequences. So we have to first create the sequence in our calculator. So remember that I have a newer one, so it's a little bit harder for me to get to it, but I'm going to do x to the 4th, and then I'll show you what it looks like. So in your calculator, I can actually just do this, I think, and show you what it looks like if I just hit the... Nope, guess not. Didn't want me to do that. Okay, I ruined everything. All right, so what you're going to do is type in x to the 4th, type in comma x, comma 1, and I'm going up to 6 because we're going from the 1st to the 6th term. It should look something like this. You don't need that last comma 1 if you don't want. And then it gives us what those are. So now what we're going to do, okay, and there's a couple different ways that we can do this. I think that we can actually just hit second list again, and this time go to math, and we're going to go to sum because we want to find the sum of something. And then if I hit second, and then this button that I highlighted way down there next to enter, which is answer, it should be put the answer there, and it will take that answer, which was the first 6 terms of the sequence, which is what we wanted to add together, and it will sum them for us. So that's how you do it on an older calculator. Hope you found that helpful, and I will catch you in the next one. Bye!